Hi there. Thank you so much for inviting me to speak to you today. I'm Carolyn Rosé, and I'm a professor of language technologies and human-computer interaction at Carnegie Mellon University. And I'm going to talk to you about viewing creativity through the lens of creative processes. Now, I know that this workshop is really about creativity. And when we think about creativity, we think about objects that are creative. We say, wow, that was a really creative solution. And I'm going to talk to you about this, I guess, as a concrete example in the area of collaborative software development. If we're thinking about the artifact, we might talk about how creative was an algorithm. And so then we're thinking in terms of the software programs themselves. But these programs were created through a process called programming. And ultimately, it was programmers who carried forward that programming process. And because I'm going to talk to you about collaborative software development, it's not just individual programmers as people that's important here. It's the relationships between them. It's the attitudes between them. It's how they relate as a result of those. And through that interaction, they create programs through their collaborative programming. So I'm going to start by talking about a kind of infrastructure in which I've been doing my work for the past 15 years, where I have been developing support for collaborative teams using intelligent conversational agents. And then I'm going to talk about how within that context we are studying and understanding the layers of creative communication between groups, even when the target of what we're trying to achieve isn't necessarily creativity as an end in itself. Nevertheless, as individuals come together to collaboratively work, they're creating something together that emerges through that collaboration that didn't exist in the mind of any one of those people before. And so by nature, it's creative. We're going to investigate those creative processes specifically in collaborative software development. And that's how we're going to make concrete these three different layers of programs, programming, and programmers. And you'll see how it is that we can study that and support that in these kinds of environments that we work on. And finally, I'll point to some resources that we can share and how we might collaborate together going forward. So let's start with those intelligent conversational agents. Here you see one of our really early setups for studying this, where we used this kind of distributed chat environment that has on the left a shared whiteboard space and on the right a chat panel. The students were working in pairs on a design task, which is a creative problem-solving task. They were trying to design power plants using simulation software, trying to maximize certain kinds of design criteria in the process. Sometimes when we ran these studies, we gave students competing goals, so they'd have to negotiate together, and that would give them more of an impetus for their creativity. Here we see in the chat as they're communicating some lines that are labeled as tutor. That's the intelligent conversational agent who's come in to offer them support along the way. And the success was shown in how we studied the ways that students learn from each other and from the support of these conversational agents in this context. Moving on from that successful foundational study, we investigated similar ideas with different kinds of support across various domains with students of different age levels, middle school, high school, and college age or beyond, in math, science, and engineering most typically, but sometimes in other areas like writing as well. In all of these cases, we're monitoring collaboration in real time so that we can offer support in a context-sensitive fashion, and we're offering it through these interactive conversational agents. Now, conversational agents, they came into these kinds of learning contexts through a history that started long before the work that my group ever did. And I want to acknowledge my late department head, Jaime Carbonell, who has been ranked as one of the top 100 machine learning researchers. In fact, his dad was also named Jaime Carbonell, and in 1970, his dad, Jaime Carbonell, developed one of the first tutorial dialogue systems to have a kind of interaction with students not entirely unlike what we were using as support for collaborative processes. So this is not a new technology. It wasn't even new 15 years ago. In fact, 1970, when this paper was published, is the year I was born. Artificial intelligence is inherently interdisciplinary, and I want to remind you of that because you need that interdisciplinarity in order to benefit from bringing multiple minds together. They should have some different perspective to bring. And Herb Simon and Alan Newell are two fathers of artificial intelligence that in themselves exhibit this high level of interdisciplinarity, but also collaborated with many researchers in a variety of fields in order to do their groundbreaking work. Herb Simon, American political scientist, economist, sociologist, psychologist, and professor, won a Turing Award, a Nobel Prize in economics, and a National Medal of Science. He worked very closely with Alan Newell, who was faculty in the School of Computer Science and also the business school, and had an appointment also in psychology. And he was a collaborator on the Turing Award that the two of them won together. History. Fields develop. Artificial intelligence can be used to support creativity. It started in 1970 with Jaime Carbonell's Scholar system. And as the field developed, so did its application in support for learning and also collaboration, leading finally to today, when we can use multimodal technologies, resting on the foundation of the same basic architecture used even in that earlier study in thermodynamics, but bringing in multiple AI technologies in order to enable even more sensitive, context-sensitive interactive support. You can see here now, it's not a chat agent, but a virtual human offering the support, and in a physical space rather than in a chat space where the students can move around, they can use a shared whiteboard, they can operate with other physical objects within the space. So that's our infrastructure. Let's now delve more deeply into these creative problem-solving processes. And at the core of what we've been studying for many years is a property of collaborative discourse called transactivity. Transactivity was motivated by a cognitive approach to modeling learning. And yet, it has been shown to be rich in interactions that are highly creative and ones that sort of really push an organization forward as they're negotiating on difficult topics. Here's an example of a transactive contribution to a software development conversation. This came from an issue thread on GitHub. It's transactive because it displays reasoning and it builds on an earlier contribution in the conversation. And at minimum, in the simplest formulation, that's how you would identify what counts as a transactive contribution. In mediation and moderation analyses of results from learning studies that have been largely experimental studies, where these analyses are used to explain the effect of an experimental manipulation on an outcome, we've seen that transactivity plays a moderating effect in expertise sharing within collaborative groups, a moderating effect on collaborative product quality, where quality depends upon an integration of ideas across multiple expertise, and also a moderating effect on learning. So over the years, we have developed a number of different design patterns for these conversational agents that offer support for these collaborative processes. They look different on the surface, but they all get at creating a setting in which the participants will stop and listen to one another and integrate their expertise and allow for difference, allow for exploration of the space, which is really at the heart of what I would say creativity really is. And one of these principles is even literally about displaying openness to other perspectives. So at the core, what we've been interested in, primarily because what's most closely related to learning, which is what drives a lot of the research that I do, is the actual knowledge building. The ideas that people build together allow the learning of how ideas relate to one another. That's a result of that interaction. But these are predicated on more basic processes of deep listening, comparing of mental models, and sharing of insights, which in turn are predicated upon respect, interest, and self-efficacy. We've already said that what comes out of interactions that are rich in this is learning, expertise transfer, and group task success, and also the experience of shared decision making. Now let's tease apart some of those layers. We won't have time to look at every one of these connections, but let's just look at a few. So we have used as a lens computational modeling to be able to investigate the connection between properties that exist at these multiple levels. So in one past study, we were looking in the audio signal from pairs that were collaborating, evidence of speech style accommodation. So we didn't look at what people were saying to each other. What we looked at is how they changed their pronunciation in order to de-emphasize those aspects of how they talked that might signal social identities that might be at odds with one another. So in de-emphasizing difference at that level, they bring themselves socially closer to each other so that they can share their different views more safely at another level, the cognitive level. So on the other side, we looked at the transcripts from the same collaborations and looked at the ideas that were expressed and how they related to one another in terms of transactivity, so that we can look to see whether there's a statistical relationship between those two. And what we found was indeed, as the concentration of signals related to speech style accommodation were getting larger, we saw a higher concentration of other oriented transactive contributions. So we had the idea, let's try then to turn it on its ear. If there's this connection between transactivity as a property of discourse and these underlying dispositions and attitudes and behaviors, then maybe if we look for evidence of transactivity in an exchange, we can predict that there is that kind of chemistry between people that would enable them to be good collaborators for one another. And so we developed a paradigm for assigning students to teams within a massive open online course, where they come into the class, they do some individual work, they present it in a community-wide discussion forum, we do an automated analysis of transactivity, then we can partition that whole community into groups of 4, so that everyone is in a group of 4, and then look at how they work together in their small groups. So we're able to use our analysis of transactivity to estimate collaboration potential for every pair of students within a community. Of course, we have no evidence of collaboration potential if they never interacted with one another. And if they did, the level that we predict can be sort of rated in terms of how rich in transactivity were the interactions between them in this context. And so then we can use an approximate constraint satisfaction algorithm to do the partitioning. To investigate the extent to which this estimation of collaboration potential worked well, we ran a simulated large online course several times in Amazon Mechanical Turk, sometimes using this transactivity maximization, we called it, to do the partitioning, and other times randomly partitioning the students into groups so that we could see whether there was evidence that doing the partitioning based on predicted collaboration potential would yield teams that were indeed collaborating better together. And when we did the comparison, we found that, in fact, it was true. When we used the transactivity maximization to partition the whole class into teams, we saw interactions within those small groups that were richer in transactivity, and also that the outcome from their creative problem-solving process was also better integrated and higher quality. Now, being able to make use of that required us to do automated transactivity detection. And you see also that the work of our modeling also allows us to tease apart these dimensions. So it has a practical and a theoretical contribution. I want to show another series of experiments for modeling transactivity that give some more insight into the construct itself. And here what we were looking at was the conceptual link between transactivity as a relationship between ideas expressed by different people in an interaction, and a more basic linguistic relation called entailment, which is a kind of really near inference. And so what we were looking at here from a practical standpoint was whether we could use very large resources that exist in language technology for the benchmark task of entailment detection to build a model that would be biased towards learning transactivity better, so that we could make better use of the small amount of labeled data for transactivity that we have. And as a second hope, we wanted to investigate the extent to which, if that foundation in entailment as a task was based on a very multi-domain corpus, would we then learn to detect transactivity in a domain independent fashion? Because it had been, a characteristic of our work in the past that we had to train a separate model for transactivity for every domain that we worked in. So we're going to train a model for entailment and build the transactivity detector on top of it using a published neural architecture for entailment detection. So what actually is entailment? Let me just give a little bit more detail on that. I said it was a near inference, a near enough inference that it's based on the dictionary definition of words. So A entails B if it could never be true that B isn't true when A is true. And it has a connection to the dictionary definition in the sense that if shoes are meant to be worn on your feet, then there must be an entailment relationship between the word shoe and the word foot. It's not like shoe and foot are really similar to each other. They might not be that close in an embedding space that represents similarity of words. But if we can shift that embedding space to make things close to one another that are related via a near inference by training on this task, then now all of a sudden the relationships might be more useful for identifying other kinds of reasoning relations between pieces of text. And in fact, it was very successful. So here, the experiment that I am showing you results from was one in which we contrasted 3 different models. At the simplest side was just a simple logistic regression with a unigram feature space. At the most complex level, our neural architecture, where we first trained for entailment using a publicly available entailment a benchmark data set, and then trained over that with about 150 examples annotated for transactivity. And in the middle, what we did was we used that adapted embedding space from having pre-trained on entailment to be able to just look to see how similar are 2 texts. And if they're very similar based on these entailment relations, we would say that they were transactively related to one another, otherwise not. We evaluated the results within domain and across domain. So the 150 examples for transactivity that were annotated as training examples were all in one domain. And we looked at a test set from that domain and also a test set from another domain. And what we see here when we contrast in domain and out of domain is that the neural model outperforms both of the simpler models and also doesn't lose performance when you move from one domain to another. This experiment is described in much greater detail in a James Fiacco paper from 2018 that was published at the Learning, Analytics, and Knowledge Conference, which I'd be happy to pass on to anybody who asks. But in our more recent work, we've challenged the ability of this model to be able to do a generality across corpora by collecting data from a much more highly articulate audience, set of participants than we'd worked with in the past. And that is students from our business school in the MBA program. It turns out when they talk to each other, their communication is very much more abstract. It's just longer and more complex. It's much more highly articulate than data from any of the groups that we've worked with in the past, really. And so we had to develop an even more nuanced definition, not this simple binary transactive or not, but we had 3 different dimensions that sort of separate this idea of active listening. So how receptive am I to what my partner is saying? Idea extension, to what extent am I building on that? And challenging views. Am I building on it to show an alternative perspective, or am I building on it to kind of extend and enrich it? So we found, because these business students were far more articulate, that the level of abstractness in their language was far higher than it was in the original entailment corpus that we had used in the first set of experiments. And so we had to identify a new corpus to use for our pre-training that was also entailment, but was more abstract. Here you can see how we're rating the level of abstractness using the same metric, basically using a dictionary where each word in the dictionary has a score for abstractness, so that we can compute an average score of abstractness for a whole text. And we see our original corpus that was from a power plant task. And the second corpus was that of our MBA students. You can see that the MBA students are higher in abstractness than the original corpus, and you can see the difference between the two NLI, so entailment corpora as well. We also looked at differences in architecture. Now, all of a sudden, with these more articulate students, they also utter much more long and complex sentences. So looking at sort of a pairwise word by word method for doing the comparison didn't really work very well anymore. You can see here that the scores are very low for our 3 dimensions when we use the same model that we'd used before, but just kind of adapted it with using a different pre-training corpus. You can see that when we went to the more abstract one, we did a little bit better, but the performance is still low. What we needed to do was use a sequence model, a transformer-based model, in order to build up a representation of the whole text so that we could take into account the structure of the articulation in how we were looking for those meaningful relationships between utterances. So the take-home message here is that we can use modeling to deconstruct this construct of transactivity as a key component of a collaborative process. We can understand its building blocks through modeling as a lens. And then you saw how it is that as we learn from our modeling how the layers are relating to one another, it also gives us ideas of how we can use the model in practical ways to support collaboration. So now let's go back to that creative problem-solving process of software development. Now, in past work in software engineering, there has been a big focus on getting software development done in a very efficient way. We want code that we get to, very well functioning code very quickly. And what has been found is that code is much more maintainable if it's modular, and it's much more efficiently built if the structure of the team is isomorphic to the structure of the code base. And this is called socio-technical congruence. And in an important past paper, it was shown that in industry, we see much more efficient software development when the collaborative team is structured in a way that's congruent with the modular structure of the code base. So building on this past work, in our work, we've been looking at open source software. And we've been looking to see, would we see a similar story with this socio-technical congruence in that context? And we found that yes, and this is also in a paper that was published recently. Happy to give you the paper if you reach out. In this context, we see that yes, in open source software, there is evidence that socio-technical congruence predicts efficiency, but it actually only explains a very small amount of the variance. And that just prompted us to dig substantially deeper into what was actually going on. And what we found is that there were cases that where the model predicted that it would be at a certain level of efficiency, and it was far more efficient. And in those cases, what we found actually was that the conversational data that we were analyzing from the issue threads showed that the work had actually already been done and that the discussion was really just reporting on work that was done. So of course it was very efficient. But what was more interesting were those cases that were far less efficient. Whereas the field has focused a lot on efficiency and modularity and actually reducing the interaction between, or the need for interaction between members of a team so that it's easier to create the situation in which people have those people around them that they need in order to make a decision and move forward. These inefficient encounters weren't bad. They were creative. They were ones where people were discussing a new vision for the software, new features to consider, new solution paths. And it took longer, but it was more creative. It was more transactive. And that started to cause us to question this idea of whether efficiency is really the ultimate goal. Efficiency pushes for standard solutions to things. Whereas stopping and reflecting takes more time. It involves more people. It engages multiple perspectives. It takes more time, but it's more creative. And so we went back to thinking about how can we study within this kind of experimental infrastructure I introduced early on, where people are collaborating online with the support of intelligent agents. Can we look at that in terms of synchronous software development? So we borrowed a paradigm from industry called mob programming that's usually done in face-to-face contexts, but we're studying it in online contexts. Of course, everything in the past year has been pretty much online. So we've been doing our studies in a 16-week project course on cloud computing that's offered every semester at Carnegie Mellon University. And it's always been an online course because it's offered across all of CMU's branch campuses. In this context, students work together in an industrial strength software development environment. Here we see Amazon Cloud9, and we've recently been working in VS Code LiveShare. In both cases, the students have a place where they can collaboratively enter code, even though they're all sitting at their own computers. And they're communicating with one another through chat. And here where you see the OPE bot, that is the intelligent conversational agent that's supporting the interaction between the students as they're doing this work. In mob programming, we see an extension of what you might be familiar with as pair programming. Similar to pair programming, we have a driver and a navigator, but we have some additional roles as well. The driver is the one who directly enters software into the editor. The navigator leads the discussion and directs problem solving. The researcher brings resources into the discussion to support reflection on alternative paths. And the project manager monitors the extent to which people are taking up their roles and interacting well together, offering feedback to the group and encouraging them along. So in the studies that we've done, we have used these roles in a rotating fashion. The idea being that what we want to be able to do is engage the expertise of the different members of the team by changing the nature of their engagement with the software. At any given moment, every one of these roles can be active, but only one person is entering code. Some people are stronger at some roles than others. And as the team rotates through these roles, people have the opportunity to sometimes be the expert, sometimes be the novice, see how they benefit from their team members, see how their team members shine in some contexts, and how they need them and how they benefit from them. And this builds up the team. But we also introduced a reflection phase, learning from what we saw in those very creative but slower interactions in the open source space. This is a place where we explicitly ask the groups to reflect, not to focus on efficiency, not to just get the job done, but to really engage with each other's minds and build ideas creatively together. So we investigated, how does this play out in this context where obviously time is of the essence? When students come to a class or when they're working in industry, they have a finite amount of time to achieve the ends that time is set aside to achieve. So in this study, it's the same story. They have an 80-minute class period to get an assignment done together. They're working together in groups of 4, where where the session is divided into a series of 4 smaller sub components of the larger project that they're doing together. And our experimental design creates 6 conditions using 2 factors. In one factor, we're varying the order within each of those 4 blocks of programming first and reflection second, or vice versa. And then at what point within that block do we do the switchover? Is it at 1/3, 1/2, or 2/3? And for success measures, we looked at how much students learned from the collaborative engagement, and also how well prepared they were for a subsequent software development effort that they would do by themselves. And what we found is that they learned more when they reflected more. That was the main result from this study. They learned significantly between pre and post in all conditions, but their learning was higher the higher proportion of the time they spent on the reflection, even though they weren't making more progress on the code. And we also saw that they were not harmed from having taken time out for this reflection in their ability to carry a more substantial software development effort on their own after that. In fact, the trend was in the opposite direction. Though it wasn't significant, the students who reflected more were actually better prepared to do the software development. So I think that bodes well for creativity, making space for creativity, supporting creativity when people come together, and how that can happen even in an industrial strength software development process using conversational agent technology. So moving ahead, we would invite you to delve more into the data that we used for the study, where we looked at these open source teams and how their processes related to their efficiency. We can also offer papers that give more insight into the studies that we have run in the cloud computing course, where we've had synchronous teams working together in this mob programming paradigm. Also, many papers about our other design patterns for conversational agents that support collaboration. And the code for the collaborative support is open source. We're happy to share that too, including our recent work in extending it for multimodal interaction. So reach out to us if you're interested in collaborating along any of these lines. So in conclusion, I would say creative processes are predicated upon dispositions and attitudes. Features visible in the language, both audio and textual, enable automated monitoring. So creative processes can then be supported by conversational agents in a dynamic way, responding in real time to what's happening in the collaboration. And we have open source resources available, so reach out if you want to collaborate. And thank you again for inviting me here.